Okay, so
we're going
to restart. So hopefully, so by introducing, so the idea is these are all smooth transitions through some geodesic something in machine learning space. And the connection between the techniques we've seen so far is principal coordinate analysis going to nonlinear spaces and computing distances in nonlinear spaces, followed by using also multidimensional scaling to compute, classical multidimensional scaling to compute distances that were built on a graph. So there's a conversation going on over there. It's obviously a good one. Oh, hello. So the smooth transition now is that now we've got these networks, these graph networks, these sparse networks. And actually, I argued that the, let's see, the graph here, to me, this is, that's the solution, actually. Everything else that follows is just messing around the corners, good algorithms, bad algorithms, for different contexts. They're all good algorithms in their place, depending on whether you've got large data, small data, so on and so forth. That's the thing you want. That's the connectivity in the latent space. It's impossible to get. So you use this proxy of connectivity in data space to say what your neighborhood relationship is. And it can be quite bad. So all algorithms I'm going to talk about now have this characteristic that they have an underlying graph and they have associated problems if these connectivity issues occur. But the next one I want to talk about is the sort of simplest of them. So Laplacian eigenmaps was a spectral algorithm, and by spectral we mean that they're going to compute the Eigen decomposition at some point of something, introduced by Misha Belkin and Pathaniyogi, where you define the same neighborhood in the data space, and then you define the adjacency matrix, where the adjacency element is only non-zero if I and j are neighbors. Now the idea is that a good one-dimensional embedding is one where latent points minimize this cost function. So this cost function is dependent on the latent points, and basically if 2 points are neighbors, this applies. Otherwise it doesn't. So 2 points need to be close if they're neighbors. And our notation we've been, that's our distance in latent space, so we'll just write that as delta ij. So there's a slight problem with that cost function. How's it minimized? By putting all the data points on top of each other. Doesn't matter whether they're adjacent or not. So what we do is we also have a constraint that they should be inflated, and that will come in a moment. But we can write this thing in matrix form as this trace. So as I say, I like writing things in matrix form of A and lambda. And I'm going to do this trick again in a bit. So I'm going to go through it quicker now and maybe slower later if there's time. But that means that we can take this adjacency matrix, multiply by these distances, and if we introduce something called the Laplacian, where we have a degree matrix, and this degree matrix is a diagonal matrix, where the diagonal elements are the sum of the adjacencies for that element. So it's basically the number of neighbors. If these adjacencies are constant, it's the number of neighbors for each data point. Sometimes you can set these adjacencies non-constant, but it's then just the sum of those weights. And Laplacian is written in this form, so it's a defined thing for a graph, that it's the degree matrix minus the adjacency matrix. Using that, this is a trick, which, as I say, I think I may have more details on later. But it allows us to go from this square distance. It's the same trick, actually, as we've been using with that centering matrix. This is a square distance matrix, and this is an inner product matrix. The reason you can pop between these two is because, let's try and show that. So this matrix delta is a distance matrix, so it has zeros along the value on the diagonal, yeah? All along the diagonal. Taking the trace of two matrices that are multiplied together is equivalent to the MATLAB dot times multiplication followed by a sum. That's the way to do it. Don't ever multiply two matrices together and then take their trace. That's extremely slow. Element by element, multiply them, and then sum both directions. That's much, much faster. One's cubic and one's quadratic. So that is the distance matrix, delta, and that's being dot times by A, which is this adjacency matrix. So A is a sparse, so you've got this delta times this sparse form, which has sort of, I don't know, let's call them ones, but they could be anything, and it's symmetric, because everything's a symmetric neighbor, and zeros everywhere else. Oh, sorry, knocked out. Okay, so because the zero's down the diagonal, it doesn't matter what the diagonal of A is. You can set the diagonal of A any way you like. Yeah? So what this is saying is replace A with D minus A, where D is a diagonal matrix. Call that L. So if you now, L also has the characteristic, because D is the sum of the rows, L times 1 is equal to 0. It's got this null space. Now that means that if we multiply L by a distance matrix, what happens? This old representation here we get these terms cancelling, and you get just this XX transpose appearing. So in rough sketch, that's a nice trick. It's also used in spring systems, which we'll mention a bit later, to turn what was a function in terms of a distance matrix into a function in terms of an inner product matrix. And this thing turns out to be quite straightforward to minimize. So the Laplacian actually has this effect of making it insensitive to translations in this form. If you have this matrix here having a null space in the eigenvalue 1, that means that it doesn't matter what x's mean is. So it's insensitive to translations. Now, that's minimized by placing all the points on top of one another. So what we do is we add a constraint, and this is the constraint they choose, which is that the inner product between each data point and the degree matrix, this is each data feature in the degree matrix should be 1. You could choose a constraint where that is just x colon I transpose x colon I is equal to 1 without the d in there. They happen to choose this constraint, which is slightly annoying because that leads to a generalized eigenvalue problem rather than the standard eigenvalue problem that we've seen. If they'd not chosen that constraint and they'd just chosen that the covariance of the embedding should be 1, which is the normal constraint, you would get an eigenvalue problem here. But I think, you're splitting hairs as to, I think that's not really making much difference. It means it's not quite minimizing the error functions we've talked about before, or when we see it in its more general framework, it won't be. So the smallest eigenvalue of this Laplacian is 0 because it's got a constant eigenvector, which is 0 eigenvalue. And that's typically thrown away, and then you retain the next q eigenvalues for embedding. And you're minimizing, as I say, this objective here under the constraint that the variance of x is, in effect, d, the covariance of x. Now, they parameterize A either by just setting it to constant values, which they call the simple-minded approach, or according to distance between two data points. So this is the adjacency element here that they will sometimes set. And it's not related why, this function appears everywhere. There's no specific reason why it should be related in this case to the RBF I've been talking about before. They motivate it by an analogy between the discrete graph Laplacian and the Laplace-Beltrami operator, which is continuous diffusion equations, which they're saying the graph Laplacian is a discrete approximation to. I haven't played a lot with this, so I don't know how sensitive these algorithms are to the setting of this length scale here, and how you set these adjacency weights, but it's something people do when they do this. So you can do those two smallest eigenvalues, and then you see embeddings like this. This one's picked up the fact that the start of that run is different, but then it hasn't quite got the nice structure in the... If you went to the third dimension, you would see probably the structure in the run there. You don't quite see in the 2 dimensions the fact that these angle of run is different here. As I say, I had to go for large neighborhoods because these graphs are disconnected, and that's meant that this is pushed back the green overlying on the red. Although you can see some nice structure in that section there that you don't see in PCA, but this has meant we had to go for these large neighborhoods to ensure these portions of the manifold were connected. And that can be a problem, obviously, with these neighborhood graphs. Gene expression, again, I don't really see anything much in that one. I'm really close to Scottish now, and I sound like our secretaries in Sheffield, apparently, as well. So again, you see there's some separation, but this is weird because Sarah, one of the PhD students in the speech group, has suddenly moved into the men. So I'm not quite sure that embedding is very good. In fact, I'm kind of skeptical about whether Laplacian eigenmaps is a good thing to do in many cases. I tell you where I think it's good is if you've got enormous amounts of data, because the eigenvalue problem you do is a sparse eigenvalue problem. Computationally, that's very quick to solve. But for very few data points, it often gives really bad embeddings. And that's because it's not putting any effort into thinking about what these adjacency weights should be. And I'll come back to that later when I try and unify the perspective. It's fast because it doesn't do anything. Okay? And now that's not a bad thing. If you think about PageRank, it's basically Laplacian eigenmaps, the Google algorithm. So you can do this on web scale data. There, the adjacency is just the linkage between different web pages. Very, very similar. So you can do this on enormous data. And if you go for enormous data, it turns out it doesn't matter that you don't parameterize the graph very much. But if on the data sets I've used here, I mean, particularly this one where there's only a few data, very high dimensional, but a few data, it's not doing a great job. So I would tend to think of using Laplacian eigenmaps if I'm going for very, very large data, because certainly for that data you can't do isomap, which I think is a really good basic thing to do. So if you see the results that, I mean, Misha has some really nice results on things like the full USPS data set, and he uses it for semi-supervised learning. So it can definitely really work in domains that I haven't sort of shown here. Locally linear embeddings. You know, I really hate this. Not locally linear embeddings, I like them. But what I hate about spectral methods is what I'm doing now, and I'm going to try and correct that in a minute. Is what I do is I stand up and then I say, oh, here's another way of doing dimensionality reduction. Imagine everything's living in a diffusion equation, or everything's locally linear, or this and this is that. And you can all nod and think, yeah, that makes sense. But if you try and teach that to undergraduates, which I think must be the final aim of any of the research we're doing, being able to incorporate it into an undergraduate course, you have to do 3 lectures on each method in order for them to understand what's going on, yeah? So it's a completely different motivation. And you get a flavor for this as I'm going through, because now this is a new way to do dimensionality reduction, which says let's approximate a nonlinear manifold by small linear patches. And it's a really nice idea. Assume distance between data points is small relative to the curvature. So if you look in your neighborhood that we've been talking about before and assume that it's linear in that neighborhood, so the curvature isn't moving quickly, then you find a set of linear regression weights for this locally linear patch, and that's this equation here. You try and reconstruct a point from its neighbors by this weighting of its neighbors. So you've got point yi, and you try and reconstruct its value by weighting neighbors of that point with a quadratic error function. This objective is invariant to rotation and rescaling of your data, but it's not invariant to translation. So there's something we're going to do to this objective. Sam Rice and Lawrence Saul proposed this and motivated, well, if we modify with a translation, so we're adding mu to all our yi's, so this is minus yj, so there's a minus mu there. If we add that in the objective, we get this form, and that changes the value of the objective. So in order to fix that, if you constrain this sum to 1, the sum of the weights to 1, that's a minus mu, and that cancels with that mu. Yeah? So that's an important thing. It's not just regression. This would just be regression in the data point space rather than in the feature point space to minimize this objective. But this is regression with a constraint. Constraint that the sum of w's must be equal to 1. You see these constraints popping up everywhere, right? The Laplacian transpose 1. So that's going to be meaningful later. It's got another. But you can see it here in the way we've written this objective here. Now the idea is you then fit these w's for each data point, for each neighborhood, and then you look across all the neighborhoods, and you start with a new data set we'll call X. And you may force X to be a low-dimensional data set. And if you force X to be a low-dimensional data set and you sum across all the neighbors, you get this, which is the same objective function, but just re-expressed in a different way. It's an objective function in X and M. Now you can rewrite that in this trace form, which is very similar to the form we saw before for Laplacian eigenmaps. I'm missing a transpose there. And you can rewrite it so that you've switched around the M's and the X's. That's sort of a little trick to show that this is actually a single matrix here, and that is very similar. If you replace that with L, that basically looks like the Laplacian eigenmaps objective. But here L is M transpose, and I've failed to define M. Sorry. So M is I minus W. Okay? That's important as well. I'm not going through this slowly because, to be frank, I'm going to unify it later with another perspective on it. So I'm just trying to show you this is the standard way you present these algorithms, and I'll try and unify it. I want to have more time later to try and unify how it fits with the other algorithms. You can see hints of it. So this M, which is I minus W, the whole matrix of W's, which is a sparse matrix reflecting the neighborhood, times I minus W transpose. If you think of that as L, this looks very similar to the Laplacian eigenmaps, but here you constrain the covariance to be 1 rather than D. Before we constrained it to be D, and you get an eigenvalue problem on MM transpose, where the smallest Q plus 1 eigenvalues are retained. This is the same objective in effect, yeah? So it's the same solution, but it's not quite clear why these two methods are related. One is a connectivity graph saying these points are connected to this. The other one is saying, oh, I'm a locally linear blah, blah, blah. We'll hopefully make that clear. So you retain Q eigenvalues and different motivations, similar process to Laplacian eigenmaps. And here we just choose not to constrain to scale by the degree matrix. But that's plucked out of thin air anyway, whether you do that or not, because it's just a constraint you put on to prevent collapsing the embedding. So I don't think that's significant. And you can look and you see, look, you get similar embeddings again. Okay, and then here we've got the same problem. We have to go to many neighbors to prevent the graph being disconnected. We see something slightly different. Same issues here. Here we don't have, oh, Sarah pops up again in the middle of the men. Okay, so that is a way too fast description of locally linear embedding with no intuitions. Good. But that's because, so it's faster than isomap, and it's slower than Laplacian eigenmaps, but it can still give poor embeddings for few data points. So that you get similar problems for, and we'll see that with some experiments at the end. But what I want to do now is talk about the last spectral method that I want to introduce, and then I want to try and unify them. Now, the depressing thing about trying to unify these spectral methods is that I had to introduce a new spectral method in order to do it. And the thing I really don't like is the proliferation of these spectral methods. Not because any of them are individually bad ideas, but just because they don't seem to sit within a framework. But the new spectral method I'll introduce will hopefully give you a unifying perspective on what all these methods are trying to do. So maximum variance unfolding is very much inspired by kernel PCA, and this feature of kernel PCA that it doesn't reduce the dimension, it actually expands the dimension. So they're trying to say, well, we're going to learn a kernel matrix that will allow for dimensionality reduction. So I don't think, sorry, I've noticed I've failed to do the time on my thing here. So I don't think this is a kernel matrix. Personally, I wouldn't call it a kernel matrix. I would call it a similarity matrix, because it doesn't have the mapping association that a kernel matrix has, but they'll talk about it as a kernel matrix. So it also has a relationship, it has these local relationships, these neighborhood features again. So what you do is you take the neighbors, and this bit's similar to isomap, and you construct a kernel matrix where only distances between neighbors match data distances. So because you've got this relationship between the kernel matrix and the distances, you can constrain your kernel matrix such that neighbors in your graph have the same distance that you observe in the data. Okay? So hopefully this makes that a little bit clearer. You take any neighbor here, and it's got its distance just like in isomap, yeah? Any neighbor with its distances, you take the distance and you say that distance d14 must constrains in the kernel matrix k11 minus 2k14 plus k44 must equal the observed distance in the data, like the distance I used in isomap to construct the graph. So you're doing a constraint on the model that the distances between neighbors should match. That's a good thing. That did not exist in Laplacian eigenmaps and LLE. And I think isomap and MVU are stronger algorithms with low data because of this feature. So they constrain that, but that's a sparse constraint. There's lots of elements in the kernel matrix where they're not neighbors in the graph, which you haven't defined how they should be. So the idea is to then actually just optimize the remaining elements of K by maximizing the trace of K. So that's got an interpretation as just blowing your data apart, pulling it apart, and that's the motivation they give for it. So you're sort of maximizing the trace of the resulting matrix, which you think of as pulling all the data points apart, but you've got these constraints on some points where the distances in the kernel matrix should actually match the observed distances. So if you do that, and then on that kernel matrix you just do classical multidimensional scaling, you get this visualization for that stickman data. And this is really characteristic of MVU. You get these little ziggies. May relate to the question earlier on Euclidean distances, actually, because you're forcing this thing in isomap. This thing is constrained positive definite. As I say, that paper at AI Stats, which I haven't fully understood yet, claims that this is the same as doing isomap with an additional constraint that these distances must all be Euclidean. And actually the embeddings look very similar, apart from these sort of little zigzags you get, which is not due to noise in the data, because this data is very noise-free. So I don't know if that's some sort of side effect by forcing the distances to be positive definite. You can't do the oil data because the graph doesn't fully connect till at least 30 neighbors are used. And then this is too slow because there's a semi-definite program, which I didn't mention, I apologize for that, to do this maximization. I haven't talked about how you do that maximization because it's a semi-definite program under constraints. And I didn't apply the approximate version of the algorithm. But you do get, you know, again, reasonable visualization for the grid vals data. And, you know, it's a method that I find works generally quite well. So it's high quality embeddings with no negative eigenvalues, but it's slower than all the other methods. So it's got, if you don't like the negative eigenvalues, it's the sort of thing to go for if you've got smaller data sets. Now, what I want to then present is, inspired by maximum variance unfolding, is a new perspective that actually unifies these things into one framework, okay? So maximizing variance is what's being done in order to sort of pull the manifold apart. So the image that Lawrence uses when he talks about this is of men pulling on a sort of, I think of it as like a tangled up mattress. So you're sort of pulling on a tangled up mattress, and then where the springs are, you can't pull it apart anymore, so you just basically unravel it. And they do that by maximizing the variance. But in this case, what I'm suggesting is, well, let's do maximum entropy instead of maximum variance. Because entropy and variance are quite closely related. But maximum entropy leads to a probabilistic model. So I'm not going to spend much time talking about maximum entropy. But then each spectral approach turns out to approximate maximum entropy unfolding in some way. In fact, locally linear embedding turns out to be a pseudo-likelihood maximization of this algorithm. So and then Laplacian eigenmaps just turns out to be, I didn't bother setting the parameters. So all these methods can then be seen from this probabilistic point of view. And I should say this is sort of research per se, but this is research that was entirely done to try and pull these methods together into a unifying framework, not for any other motivation. So maximum entropy constraints, you find a distribution in maximum entropy. It's a way of looking for distributions subject to constraints on the moments of those distributions. And the moments we're going to use here are the expected squared distances. Yeah? So whereas before in maximum variance unfolding, we just put these distance constraints in, this is the difference between these things. Here we're not defining where the moments are coming from yet. We're just saying that the distribution, which is a P of y, it's going to be a probabilistic model, P of y should be such that the moments under P of y give me the observed distances in the data for the neighbors. Is that clear? I should pause at this point because it's kind of crucial. And I know, because I'm constrained for time, I've gone a little bit quicker than I'd really have liked over the last little bit. So we're going to look for density such that when we sample from the density, the expected squared distance equals the observed squared distance. That can be written in terms of the covariance of the density. Doesn't matter what the density is, it's always writable in terms of the covariance, which is exactly the same constraint we've seen before, whether that's a covariance matrix, a similarity matrix, or anything else. So you see the same theme emerging as we saw in kernel PCA, so on and so forth. We're just, in effect, specifying that. We don't know what the covariance will be yet. Maximum entropy, as defined by Jaynes, is a really lovely sort of framework where you just include Lagrange multipliers on the distance constraints. And you also need to include this slightly annoying thing called a base distribution in continuous case. So this term here on the left is called the base distribution. And it's actually, in this case, it's just a Gaussian with a very large covariance, spherical thing. Try and ignore it. You can actually take that thing to 0 and make it disappear, but things aren't formally correct then, but it still sort of works. But what you do have is Lagrange multipliers associated with all the distance constraints. So this is the sum over j for all neighbors, where j is each neighbor of I, and the sum over all I, with a Lagrange multiplier on every distance constraint. And this is just the form. All I'm writing down here is the known solution for maximum entropy that emerges from applying moment constraints. So you can look this up in maximum entropy textbooks. But what's nice about it, again, is you can rewrite this in one of these forms, where this is the matrix of all distances, and this is lambda. These are the Lagrange multipliers, which is sparse. In fact, it's the same as that adjacency matrix we've had before. So you end up with this spherical term, this term from the base distribution, and this sparse term of Lagrange multipliers. And you can use that trick that I outlined to convert that in from... It's really difficult when you start dealing with Lagrange and Laplace. So this is a Laplacian, which contains the Lagrange multipliers. So this is the same trick before that we keep using, actually, to move between the trace of a multiplication between a distance and a sparse connectivity matrix and a Laplacian and an inner product matrix. So I briefly outlined that on the board there. And the reason you can do that is because the Laplacian has this null space. Now, this Laplacian is the same as the previous Laplacian, where the off-diagonals are the Lagrange multipliers now, rather than these adjacency elements which were set constant or set according to some Gaussian function that we had before. And the diagonal is just the sum of the off-diagonals, giving us the standard Laplacian form. You also get, note you also get this term appearing, yeah? So this gamma needs to be combined into here, and there's a gamma I appearing there. That has the effect of making it a proper probabilistic model, because the Laplacian has a null space in the constant eigenvalue, so in the constant eigenvector, so it's not a valid inverse, well, valid, as this will turn out to be the covariance. So this is why the base distribution is needed. But you can consider the limit as that gamma goes to 0, and also gamma doesn't affect the eigenvectors, so it doesn't affect any of the later analysis. But this is the maximum entropy distribution. And this is, in fact, a Gaussian random field. So it's a Gaussian random field. The covariance of this thing is the inverse of this sparse model, of this sparse Laplacian, yeah? And then there's a determinant there to normalize. So, okay, here's just the review of how you move between those two representations. Minus trace of the Lagrange multipliers times the distance is equal to, in our definition, because the diagonal of the distance is 0, trace LD is unaffected by the diagonal of L, is equal to the trace of L times D, because we've set the elements of L off diagonals to be negative Lagrange multipliers. And this is just the sort of little proof I was doing before. So, because that's the case, you can cancel those two terms and recover that. So, maximum entropy probability distribution under these distance constraints between neighbors is a Gaussian random field. Gauss-Markov random field with this covariance here. But the one thing I want you to notice about it is it's independent across data features, not data points. Now, I love models like this because they just blow away all the standard statistical analysis that people tend to do and show that a lot of it is nonsensical because it's just about model definition. It's a funny thing to do because you're saying, instead of saying independence across data points, you're saying independence across data features. But this is emerging from maximum entropy. I haven't made this up. I've said, please give me that distribution. And it just gives me independence across features. So I'm not sort of, this is emerging just from the maths. So L is the Laplacian matrix associated with a neighborhood graph that we've already seen before, and the off-diagonal elements of this Laplacian were the Lagrange multipliers from the moment constraints. So the Gaussian random field is specifying these independence across features, but most applications of Gaussian models are applied independently across data points. So people who've done this differently, this is Zhu and Garamani and Lafferty, who looked at semi-supervised learning. Myself with the GPLVM I'll talk about next time, and Charles Kemp and Josh Tenenbaum have looked at these sparse Gaussian random fields in the context of cognitive science. Now the point about maximum entropy, if you're not familiar with it, is that if you want to know the parameters, the Lagrange multipliers, it's always equivalent to doing maximum likelihood. So these two things are equivalent. So maximum entropy knowing the Lagrange multipliers is equivalent to maximum likelihood in this model. But there's something funny about maximum likelihood in this case, because there's something I call the blessing of dimensionality. So everyone knows that if you have large p, small n, that's very bad. Because what happens is that your parameters become badly determined. You've got order p parameters and only n data to determine them. Maximum likelihood is consistent. As we increase these data points, the parameters become better determined. The way you demonstrate maximum likelihood is consistent is by looking at KL divergences between the true distribution you don't know and your approximating distribution. You assume your approximating distribution is in the class of the true distribution, and you show that you can get a sample-based approximation to that KL divergence, which is the likelihood. As that sample-based approximation gains infinite data points, you will recover the true KL divergence minimization. That's not true here because the sampling is being done across data features. So this is consistent as you get infinite data features for a fixed number of data points. In this case, when that man comes into your office saying, I can give you 100 extra data points about that case you're interested in, you go, no, no, that will make my parameters less well determined. Don't give me any more data points. That's the converse to the guy who came in saying, here's 100 extra data features. So the blessing of dimensionality, which is exactly the consequence of analyzing a model that's independent across features, shows you you want many, many more data features, and you don't want any more data points. So it's exactly the opposite lesson from the normal curse of dimensionality. Of course, it's all a little bit of a joke because it's just about your model definition. It's nothing to do with your data. So I think that a lot of those ideas about large p small n being a problem should be put to bed because they're consequences of old types of statistical analysis. And it becomes really clear for these models. If you are into large p small n, you should use a model like this. This model will be very well determined as p goes large. And it's interesting that all the dimensionality reduction algorithms I've just been presenting are effectively trying to approximate or doing something like this. So they are well determined as the number of data features goes up. In fact, that Swiss roll example is a nasty example because its P is 3 and N is 3,000. And if you do locally linear embeddings on it, if you've ever applied that, you have to introduce a regularizer if your neighborhood graph goes above the data dimensionality. You have to regularize it in this domain where P is 3 and N is 1,000. That's freaky. Why is that? There's your answer. It's the wrong domain. It's not what you should be looking at. You should be looking at a Swiss roll in 50,000 dimensions, not in 3. Of course, it's hard to plot 50,000 dimensions in a science paper, but that's why they do it. So as we increase the data points, the parameters become better determined normally, but here as we increase the data features, the parameter become better determined. This is completely turning the large P, small n problem on its head. And it's, so it's the blessing of dimensionality. But actually what it's really saying is that is not a characteristic of your data, P and N. These are a characteristic of your model and how you're choosing to fit your model. Don't fit models which will lead to badly determined parameters. So there's the sort of difference between the two types of modeling. Curse of dimensionality, blessing of dimensionality. Curse of dimensionality, blessing of dimensionality. And this becomes really clear if you work with things like microarray data, where it's not always clear which is P and which is N. Because sometimes you're interested in different data points being the genes, but sometimes you're seeing those as being the data features. Depends, are you interested in, and the experiments are the features of the genes. So you can try, it's just a matter of transposing these matrices and fitting them the other way around. Of course, it does lead to some practical consequences. In this model, it's very easy to include or predict for a new data point, a test data point. Very easy, yeah? Because it's just independent. And you've got the parameters. In this model, it's not easy to predict for a new data point, because you need to compute the extra row and column of K. That's why it's difficult to embed new data points in all these algorithms. They actually tend to work with a fixed number of data points. However, it is trivial to introduce a new data feature. So that's something we're not used to thinking about doing, because normally we work with parametric models. I fit a model, so I'm going to classify all you people here as, I don't know, what I classify you as something. I classify you as friends or enemies, yeah? And every time I see one of you, I classify you as a friend or enemy. I have data about you. I know what your likes and dislikes are, yeah? But what happens if I find out a new bit of data about you? What do I have to do in the standard parametric modeling framework? I have to learn a new model. So if you all sort of say, if I'm asking questions and deciding whether I like or dislike you, and then I say, do you like football? And add a new feature, how do I accommodate that within a model, which is a classic independent across data points? I can't, not without refitting the model. But in this model, I can, trivially, just as you can introduce new data. So for a fixed number of people in this room, this is the right way of doing it. If someone else walks in the room, then I have problems. I have to refit this model. But for that model, every time I ask you a new question, I have to refit the model. So the point the lesson from this bit is, just because you were taught things in a certain way, that doesn't have to be the way you think about things in the future, because large computers and so on and so forth mean that things are slightly different. This is away from the classical way statisticians will teach you things, and I think it's much more interesting to think in these ways. Consequence of model definition. There are problems by doing models that way, as we've just described, but there are also some things become easier. So what's going on here, another point about this is the covariance interpretation we were looking at before about how we get the distances from these models. What we now know is this is our new kernel matrix. It's the inverse of that Laplacian we saw before. So in all these models, what we were doing with kernel PCA and MVU is we were doing an eigenvalue decomposition on K, taking the largest eigenvalues. Now, we're seeing that the Laplacian is the inverse of K plus a diagonal constant that doesn't affect the eigenvectors. So what that's saying is, right, okay, Let me skip that because I was going to talk about, I didn't realize I had that bit next. And I'm also short on time. So the Eigen decomposition of the covariance is this. The Eigen decomposition of the Laplacian is that. Okay? So how are these related? The eigenvectors are the same, but the eigenvalues are 1 over each other. And there's also this annoying little guy. But he doesn't affect the eigenvectors. He has to be there for the maths. Principal eigenvalues of K are the smallest eigenvalues of L. So in other words, when you're doing the smallest eigenvalues, as in Laplacian eigenmaps and locally linear embedding, you're just doing the same thing you were doing in kernel PCA and maximum variance unfolding, but you're operating on the Laplacian. Now, why is operating on the Laplacian a good idea? Anyone?
You don't need to compute the inverse.
Oh, where did that come from? That was weird. Yeah, you don't need to compute the inverse, but actually you don't need to compute the inverse to do an eigenvalue problem anyway. Because once you've got the eigenvalues, the inverse is just a matter of inverting the eigenvalues. But you don't need to compute a dense eigenvalue problem. So because of power methods and so on and so forth, eigenvectors of this are easy to extract. Eigenvectors on this are slow to extract. So you should, if you can, operate on this. And what this, I mean, I haven't worked this through for maximum variance unfolding, what the implications are, but it would be really nice if you could, in maximum variance unfolding, never specify K fully. That's why it's slow. You've got to specify the full matrix K, which is actually dependent on some sparse network underneath. It's a nice algorithm, but it's slow as a result of that. Isomap doesn't quite fit into this framework, does it? Because Isomap, we never actually looked at we never defined the probabilistic model. We didn't look at the Laplacian. What goes on in Isomap is you're filling in, you can work out what the implicit K was, but you're not filling in the elements of K by maximum likelihood or anything, as I'm suggesting here. You're just filling them by shortest distance on a graph. Turns out, I'm short on time, so I don't have time to go into the details on this, but the distances that are associated with these models are effectively random walks on those graphs going across all possible routes and the sum across all diffusion distances on those graphs. So in one case, for the Laplacian models, the distances that are implied are the distances associated with summing across all possible routes in the graph. In Isomap, the distances are the shortest distance between 2 points in the graph. So that's sort of how they're related. But I'm short on time. So I think we've seen how Laplacian eigenmaps is related. We're just not fitting the parameters of that Laplacian. But the cool thing is how locally linear embedding is related. And this is the last thing I really want to spend a little time on. So the Laplacian needs to be constrained positive definite. And that's not always easy to do, but this is my favorite trick for constraining a matrix positive definite. Just write it in the form of two other matrices. Here, this isn't low rank, this is n by n. But what it could be is sparse. And what we also can do is, in order to constrain it to be a Laplacian, we can force m transpose 1 to be 0. Okay? So this is just a way of constraining the MEU model so that the Laplacian is positive definite. And once we've done that, we end up with this result that the diagonal must equal the sum of the off diagonals. Now, locally linear embeddings are then a specific case of maximum entropy unfolding where, first of all, you constrain those diagonal sums mii to 1. Remember, the sum of w's was going to be set to 1 instead of allowing it to vary. And you find the model parameters by maximizing the pseudo-likelihood of the data, not the real likelihood. That's typically a fast way of fitting a Gaussian random field. In fact, pseudo-likelihoods are originally proposed by people working in spatial statistics who are fitting Gaussian random fields. So the proof of that, quickly sketched, is that for our unit diagonals, we have m is I minus w. That's the form that you get in locally linear embedding. And the off-diagonal sparsity of w matches m. So you end up with that being true, which is true in LLE as well. And LLE says that you should look for the smallest eigenvectors of this guy, which is equal to our Laplacian. So that's exactly the same as what we'd suggest to do classical multidimensional scaling. And it's like Laplacian eigenmaps as well. The other portion is the pseudo-likelihood approximation. And that says that the joint distribution is approximately equal to the product of the conditional distributions in the graph. So these are all the conditionals. Now the true likelihood is proportional to that, but it's got a normalization, which is in the Gaussian case, it's the determinant of the covariance. And in pseudo-likelihood, that normalization is ignored. So this is the pseudo-likelihood of this model. Now, if you cross out that bit and look at the log of this, that was exactly the objective for locally linear embeddings. The new bit is this term here, which doesn't appear in locally linear embeddings, and that's the precision of each of these Gaussian fits. Okay? So locally linear embedding fits them with a precision of 1. Basically pre-describes what that should be. Here, that comes out of the maths as well. Okay, so LLE is approximation to maximum likelihood in this new model I showed. But important point about LLE is actually the sparsity pattern. Because the sparsity is done in W, not in the overall matrix, you don't get the same neighborhood graph in the final graph Laplacian. And in fact, it's NP hard to work out what the sparsity pattern in W should be in order to get a desired sparsity pattern in L, which is kind of annoying. So you always end up with slightly different neighborhoods. So here's a point which really illustrates that something funny was going on in LLE, which turns out to be the pseudo-likelihood. So locally linear embedding is motivated by considering locally linear embeddings of the data. But interestingly, as we increase the neighborhood size k to n-1, we don't recover PCA. So if you're going from a local to a global linear embedding, you would expect to cover PCA because it's optimal. But in LLE, you don't. And the reason you don't is because it's optimizing the pseudo-likelihood. In contrast, if you do the same thing in this maximum entropy unfolding, if you do the same thing in maximum entropy unfolding, maximum variance unfolding, or isomap, you recover PCA. You don't for locally linear embeddings and Laplacian eigenmaps. So that should give you a warning about those methods. They're not actually doing the optimal thing in the linear case. So they want me to stop. Okay, so I think I've covered those guys. So just to finally show you what the effect of that is, I'm going to combine that Stickman data set together and show you the results from all those guys. So here's the Laplacian eigenmaps we've seen before, locally linear embedding. They are quite similar in characteristic. They're just rotated by 90 degrees. Here's isomap, maximum variance unfolding, which have these similar characteristics apart from the zigzags. So you've seen these before. And here's maximum entropy unfolding, which sort of somehow looks a bit like that, but also a bit like that. It's like a mix between the two. Now, what I'm showing at the end here is a score, which was suggested by Stefan Harmeling on the quality of these embeddings for that data. The score is map from this space to the original data using a Gaussian process. Optimize the likelihood. So what you should say is if this is a good representation of the data, you should be able to predict your data from it. Yeah? So you can use any regression model, but my favorite is a Gaussian process. So you map from this latent space to the data space with a Gaussian process, and the score is the likelihood of that mapping. Yeah? So that tells you how good this space is at predicting your data with a nonlinear model. And under those scores, the methods that worry about distances score high. The methods that don't score low. Of course, these methods are not applicable to 1 million data points. That method is. So I don't want all the conclusions. I'm driving it by looking at small data because most people look at large data. But I don't want all your conclusions to be based on just that. So here's another data set. This was the one I haven't shown before, but it's a robot navigation, a robot measuring signal strength from different Wi-Fi access points. It's a 30-dimensional data set from Brian Ferris. And you expect the inherent dimension to be 2 because the robot's just moving around on a plane, seeing the signal strength of these access points. So we can apply both models again. In fact, Laplacian eigenmaps and LLE kind of fail. This data is much noisier, so the graph, the underlying graph, is pretty poor. But isomap does a very nice job. That's, I think, probably the best embedding. Maximum variance unfolding does this characteristic where it seems to put in more noise in the data than there actually was. Isomat doesn't see that noise. And I think that's to do with the positive definite constraint, but I haven't thought through the details of that. And this is that MEU thing. So I'm not trying to propose, don't think I'm trying to propose you should run this algorithm. This is a unifying algorithm that shows context. It's a context-giving algorithm. Maybe it's a good algorithm. I don't know. I didn't design it to be a good algorithm. It's for context. And then the likelihood scores, these guys do very badly again, and these other guys do well. So the final thing to say is a new perspective on dimensionality, spectral dimensionality reduction, where there's 3 stages. First, the neighborhood is selected, and I've argued that's the most important stage and the one that's the same for all these, and actually, you know, often we're getting it wrong, probably. But once you've done that, you feed interpoint distances between neighbors to the algorithms which provide a similarity matrix, and then you do CMDS on these things. Now, these are 3 separate steps. The final CMDS step is how you choose to visualize the graph you've built. You don't have to visualize it with its eigenvectors. There are many different ways of visualizing graphs. There is an entire literature on it. Feel free to go out and read it. I mean, it's important for if the stuff isn't Euclidean. You can visualize, I mean, you don't visualize a graph by its eigenvectors if it's not a planar sort of graph. So that's point 3. You can visualize these things in different ways, not just by the eigenvectors. Point 2 here is the way you compute the entries in the similarity matrix is differing. And all the sort of machine learning contributions are about different ways of doing that. And point 1 is, well, how you select the structure of this graph. You're doing that right at the beginning. You're not merging the structure of this graph with any of these other steps. So I think there's a myriad of different directions you can go in once you see these 3 separate steps. So some of these algorithms conflate steps 2 and 3, and they gain a computational advantage for doing that. So it's worth doing it because of that. And I think the last thing I just wanted to say is, one thing that makes me very sad whenever I talk about this stuff is that unfortunately both of these guys aren't with us anymore. And I mean, certainly Sam I talked about with some of these ideas before they were finished, and you know, it's a great shame that you don't get a chance to talk about it with them now. And Partha, I remember from doing NIPS program committees with Bernard on him, you know, he was very wise, and both of them have significantly influenced my thinking on spectral dimensionality reduction. And it's a sad consequence of being in the field for 10 years that you actually start losing people. Anyway, so at the end there's some references. So questions? Sorry, I've overrun a bit.
So if you have incomplete set of similarity measures, I mean, can you apply any of these things, or what do you need to do?
So incomplete, you mean missing elements? Yeah. Missing elements in your similarity measures, it's going to lead to problems when you build the graph initially. I think it's not something I've studied, but I think Madhya Kent Bibi talk about ways of filling in elements in the similarity measures. It's not something that I've studied, but that may be more for iterative MDS. So I think people have looked at that. I'm not sure how they're doing it, but it is a problem. It's also a problem, the one I've thought about a bit more, which is if you've got missing features before you compute your similarity measures. And that also messes up these algorithms too, because they kind of assume you've got a fully complete matrix of distances. I suppose if you've got missing elements in your similarity measures, you would just have to not assume that those 2 points were neighbors. That's one thing you could do, but it's a bit clunky. I haven't thought too deeply, because the design of this probabilistic algorithm was really to unify the other algorithms. I haven't thought too deeply about implications for how you might use it to deal with missing data. The main problem with that is, I think, step 1, learning the structure. You have to do k nearest neighbors in the first place. So even if this bit doesn't rely on having full complete data, you've got to deal with that bit as well. But I think there's arguments that you should be doing that bit together with this bit as well. I haven't thought too much about the implications.
Is there any place where restricted Boltzmann machine or something like that would fit in the unifying framework?
Restricted Boltzmann machines.
You know, where you have a function
Yeah.
that maps into a smaller dimension, and then you try to map it back to the original.
So Jeff tends to talk about, he likes the idea, and I kind of, you know, when Jeff says it, I believe him. He has that way of him. That actually, he believes in dimensionality reduction, but the way he believes it should be done is by a sort of parameter explosion. And then the low dimensional space is the energy function in that parameter explosion, which is actually going to relate to what Mark's talking about, where you've got low dimensionality in your parameters. There are definitely latent variables. I don't think it fits in this unifying framework. It's definitely a latent variable model, but I think he tends to like the idea of increasing, certainly as he builds layers on the top. This is what these people do. They increase the dimensionality, which is kind of more like kernel PCA, what that's doing. I think it's a good thing to do as well, for different reasons as why reducing dimensionalities. Any other questions? People just want coffee? I thought the coffee wasn't that good, actually, so I think we should just do more questions. Okay, I apologize for rushing a little bit. There's more material here than I could really get through. But I wanted to make the next session purely about the right way of doing things, which is being probabilistic from the start. I say right. I mean, I'm always, take everything I say with a pinch of salt. There's lots of good reasons for doing things this way. But my own, why I got into, I mean, I got interested in these models in like 1996 when I first started machine learning. And I was always interested in the probabilistic perspective, which is what we started with. So we're going to return to that and look at nonlinear dimensionality reduction methods, which are based on probabilistic models from the ground up, rather than putting a probabilistic model on at the end. Okay? Thanks.